So this is going to be my launching point, okay? But I need to rework this a little bit. Now, the thing is, there is a t in there. I just haven't written it so it's obvious, right? What is velocity after all? It's dx on dt, right? So there's a dx on dt hiding in here. You might say, but that's no good. This is not with respect to time. You're right. But you can turn this thing upside down and work with it. Okay, so let me rewind a little bit. Let's come back to this. The first thing I'm going to do is turn this into, this is part B now. The first thing I've got to do is actually get a velocity function out of this, not a velocity squared function. Okay, so what's v equal to? Plus or minus square root 2x cubed. Okay, now this is kind of weird. This is kind of weird because if I put in a position for x, right? This equation is currently telling me I have two velocities, and they're going. Now, I'm not going for quantum physics and superposition at the moment. There should only be one velocity for this object. Okay, so which one is it?
It's the negative one.
Ah, so I have some more information which I can squeeze out of these initial conditions. Do you notice this? This, which I've already used, actually gives me sine. Do you notice that? Like, oh, when x equals 1, that's what it is. Not this or the positive, it's only this one, right? So I can say out of this, but when x equals 1, I'm just gonna say it again, even though I've said it like 3 lines earlier. I'm invoking it again for a different reason, right? So if you like even, I could have said v is negative. That's the important thing to me about negative root 2, that it's negative, okay? Therefore, v must be this case. Does that make sense? Okay, this is good. This is progress, right? Remember we said now we've got our actual velocity function. Velocity is, after all, dx on dt. Now, what I've got on the right-hand side here, this is minus the square root of 2x cubed. It's a bit of a mess. I'm going to write it a little bit differently. That's an index form. Anyone want to suggest to me why index form might be a handy thing to use in this case? I'm about to integrate this, right? Before I integrate, by the way, there's one more thing I have to do. I have to take the reciprocal, right? I can't integrate with respect to time at the moment because this is not with respect to time. So I'm going to take the reciprocal. That's going to allow me to access this with respect to displacement. That's good. Reciprocal of the left means reciprocal of the right? So I'm going to get a minus 1 on root 2. What happens to the index, to the power, if you take a reciprocal sign? So the reciprocal of x in index form, right, is x to the negative 1. Cross the line, change the sign, that business, okay? So the reciprocal of x to the 3 on 2 is not x to the 2/3. That's making that the reciprocal. I want the reciprocal of the whole thing, which is x to the negative 3 on 2. Okay, easy trap to fall into. Can you tell that I've fallen into this before? All right, now, what am I going to do with this? What am I going to do with this? I want to, now this is interesting, right? Because I'm trying to get to x as a function of time. The next thing I'm going to do is not going to give me x as a function of time. It's going to give me time as a function of x. But that's okay, because I know lots about inverse functions, right? I've been working with these things back and forth. If I can get t as a function of x, I should be able to go in the other direction. Okay, so let's do it. You're going to integrate over there on the left. Just be careful here. That minus 1 on root 2 is just a constant, so I'm just going to write that there. Tell me what to do with this.
Raise the power.
Okay, I'm going to raise the power by 1.
And then you divide by 1.
And I divide by that new power, right? Dividing by negative a half should be the same as multiplying by a negative 2. Do you agree with that? Did I do it right?
Yeah.
Yep. So I've got some negatives that cancel. 2 on root 2, of course, is just root 2. And this is, well, that's on root x. What do you think?
Plus c.
Yes, thank you. Okay. So I've done my, I should call out something else, shouldn't I? I've done my integrating. It was an indefinite integral. There were no boundaries anywhere. So now I have to try and work out this second constant. How do I do that?
When t equals
To 0.
Aha! So this little line here, right? There's so much packed into it, right? You can really squeeze a lot out. You've got a t equals 0 and an x equals 1 that you can use at the same time. right? So there's, just can I point out, right? 3 quantities, but we've consistently used them for different reasons and different combinations, right? So let's go ahead and evaluate when t equals 0, x equals 1, therefore, what do we got here? Root 2 on 1 equals 0. Yep.
And negative root 2.
Does that look good? Yep. So therefore, time is root 2 on root x. Take away root 2. Okay? So, excellent, we noticed, yes, we're not finished. We have time as a function of x. I want x as a function of time. So what would you like me to do next? I'm going to rearrange. Yep, okay, so I'm going to add root 2 to both sides. That'll give me, I might as well put this on the left because that's where it's going to end up. T plus root 2. Now what would you like me to do? I'll take the reciprocals. Get used to taking reciprocals and checking that you're doing it right as well. Like things like this are easy to muck up. Now what?
Multiply root 2 to both sides.
Just multiply through. And one last step. I'm going to square. Fantastic. Okay, we got there, right? I got v squared as a function of x. I use that as my bridge, right? Remember I said to you, okay, when you see parts, they almost always are trying to lead you in a particular direction. And getting v squared is the step to getting v and working out which one is the actual case. Okay? Briefly describe the motion. Briefly describe the motion.
That's t approaches 0.
What would you say about it?
X approaches 0.
Okay, so firstly, I'm going to start the description. Therefore, the particle object. I didn't even tell you what it was. I'm going to say particle. It begins at x equals 1. Less. Which direction does it start moving at that point? It starts moving toward the origin. How do I know? Because the sign is negative, right? The sign is negative. So I've started over here, and I start coming back, okay? So the particle begins at x equals 1 and moves toward the origin. In what way is it moving? Is it getting faster, getting slower? What's it doing?
It's getting faster.
It's getting slower.
Getting slow.
How do I know? Where do I get this from?
It's a power.
Oh,
The original
It looks like this.
equation.
What do you reckon, Brent?
As it gets closer, the x value is smaller, so its acceleration is smaller as well.
Okay, so right at the very beginning, right? Firstly, the closer you get to the origin, because remember, you're at x equals 1 and moving that way, so x, displacement's getting smaller. So the acceleration is getting smaller, right? What effect does that have on velocity?
It gets smaller as well.
It's also getting smaller.
At a faster rate.
Hold on, what's going on? This is where you got to be careful with acceleration and like slowing down, all that kind of thing, right? Look with me. This is always negative. Do you agree?
so it's
It's always negative, right? This is always positive. Do you agree?
Yeah.
So this is always heading, it's always moving to the left toward the origin, but it's always going to be slowing down. It's always going to be losing speed, okay? Where does it stop? Does it stop?
It becomes like stationary. What? So there's no acceleration.
What would it mean for my particle to stop? If something's not moving, displacement's not changing, right? There's some point you get to, it's like, you're not going anywhere now, right? As time progresses, at what point does this thing stop? Stop changing? It never stops changing, does it? As t gets bigger and bigger and bigger, I mean, it's not changing very much, but it is changing. It's a different value, right? So this thing never stops, okay? It moves towards the origin, always slowing down. It's always slowing down because the acceleration is acting in the opposite direction to the velocity, okay? Velocity is negative, acceleration is positive. Always slowing down, but never stopping. Okay. Now, I'm going to ask one last question of you. One you've kind of already answered in a simple way, but I want you to think about it in a more physical way. Do you remember when we were having a look at this guy over here? we established, oh look, the velocity is negative, right? And I just said to you, oh yeah, of course it's always negative. But hold on a second. How do we know, like up here, right? Just because at a particular point in time, x equals 1, right? How do we know it doesn't hop over to the other side of the origin, right? How do we know that x never is negative? How would you argue that? What do you recommend?
So for that to for v to even reach 0, so to like stop essentially, it needs to be when x is equal to 0. However, you've proven here that x can never be equal to 0 because of the way the displacement function works. So as a result, it will never hit 0, and thus it will never go past 0 either.
Okay, very good. Pause for a second. See if you can understand what Reynard just said, right? We earlier on, we looked at this, and the way we said, okay, it has to be this case, it can't possibly be the other one, is we argued from this single point, okay? But once you know that, right, it's like we started here. You've got to go from there. This is not like some magical teleporting particle, right? It's got to move from there to other places. Now just imagine, let's just imagine that he wanted to move from there and he wanted to get to the other side of the origin. Why did the particle cross the other side of the road? What would he have to do? Here's my imagined axis, right? So there's the x-axis. There's 1 where I begin, okay? So in order to get from 1 over to this side, right? Clearly, he's got to pass through 0. Do you agree with that? Right? But what happens at 0? We actually already know exactly what happens to the particle at 0 if it could ever get there.
It doesn't move.
It doesn't move. No velocity. Look, put an x equals 0 into there. No velocity. But not only that, importantly, no acceleration. Right? So at the origin, you're not moving and nothing's making you move. Right? There's no acceleration acting to actually change the velocity. So once you get there, you're there forever. There's no way you could actually hop over and get onto this side of the origin. Yeah.
And how can you say that it's slowing over and then stopping? It doesn't stop at the origin.
Well, it never actually gets there. Right? This is just like a half plus a quarter plus an eighth plus a 16. It never gets to 1. Right? It keeps on getting closer and closer and closer, but it never actually gets there. It'd be 2 if it was 1 plus a half plus a quarter, but I started with a half. Okay. So therefore, this is limiting behavior, right? It can never actually go there. You can say as time approaches infinity, if you want to think about it as a limit, it would get there. But once it does, it's stuck. Once it gets there, it can't progress any further because velocity 0, acceleration 0, that guy's not budgeting. Okay? All right, so I hope that makes sense. The trickiest things that we found, we're trying to progress from here and trying to work out, well, you've got to get time back into this, right? How are you going to do that? You have to recognize there's time hiding within velocity and acceleration. So you just have to know when to pull it out, and then calculus takes care of the rest.